strategies, we would have to eliminate those strategies which are not best responses to some strategy overall. Okay. But we also can do the similar elimination iterative elimination process. Any questions up to here? Now, how we define that formally? So for each player I, we will define a sequence of subsets of his strategies in the following way. So the sequence may be infinite. The first element in the sequence would be the set of all his mixed strategies. And then we would refine that set as we proceed in the sequence. Say, a kth elements in the sequence would be given as follows. Say, you would look at all the strategies of agent I in the previous set in the sequence, which are best responses to the strategies of the opponents. Okay, but what are the strategies of the opponents? So you would look at all the strategies for which there exists some combination of strategies, some S minus I, of the opponents of player I, which belongs in the convex hull of the previous sets for the other players. What is a convex hull? Is we spoke about a convex set last time, right? You remember that. So if the convex hull of some given set is the minimal convex set that contains the given set. Okay, so if we're given some convex set, then his convex hull is exactly the set itself. If we have something which is not convex, then the convex hull of it would be the minimal set that contains the given set. Okay, so we look at the sets in the previous step for all the other players. Okay, we take the convex hull of those. We take the Cartesian product of them. That would give us the combination of strategies for the other players. And then if there exists some combination of strategies of the opponents to which our strategy is the best response, then these strategies will survive the next step in the sequence. All right? Is that clear? No? So you start with, once again, you start with all your mixed strategies. Okay? And then you look at the combination of strategies of the other players. If your strategies, and you check the strategies one after another. Okay, well, that's a continuum of them, so you're not physically doing that, but that's the definition of strategy survival elimination. So each strategy to which there is some combination of the opponent strategies where our strategy is the best response will survive, will be part of the next set in the sequence. So those sequences go and shrink. And this way we always check the strategy if it's the best response to the combination of strategies of the opponents in the previous step. Okay? And then the set of rationalizable strategies for a given player would be the intersection of all the sets in the sequence. So basically the smallest set. So that is a formal definition. Any question on rationalizable strategies? So in terms of computation, what we will do here, we will use the characterization of these strategies for two-player games. So you should remember that this is the set of strategies that survives elimination of dominated strategies. We are not going to work with the direct definition for one-player games. Questions? Another solution concept and very popular recently is correlated equilibrium. Have you heard of that? Ever? So that's a generalization of the concept of Nash equilibrium. It was introduced by Robert Oman, another Nobel Prize winner, but quite recently in game theory. And some people, some other Nobel Prize winners actually said that correlated equilibrium probably is the most fundamental solution of games. Roger Myerson, who is the big name in mechanism design, as you probably already know, said that if there was intelligent life on other planets, then the majority of them would discover correlated equilibrium before Nash equilibrium. So what's the idea there? So in Nash equilibrium, let's think mixed strategies for now. So in Nash equilibrium, if each player plays a mixed strategy, then each strategy profile is played with the probability which is given by the product of their marginal probabilities of playing the corresponding view strategy, right? So it's assumed that that the events of choosing the particular strategy are independent for different players. But we can talk about joint probability of each of the profiles being played, which are not necessarily independent, which are not necessarily products of marginal probabilities for independent players. So these probabilities can be conditional on the play of the others. Say if we look at the example of Battle of Sexes, then in this game I think we computed it to compute max-min strategy last time, but that is the Nash equilibrium as well of the given game by the minimax theorem, as you remember. So the unique mixed strategy Nash equilibrium in that game would be 2/3, 1/3 for the first player and 1/3, 2/3 for the second player to play their strategies. And the expected payoff for each one of them is 2/3. But now assume that the players together, they can correlate their action. They flip a coin together, and if the coin shows heads, they go to the theater together, it's probably half. And if the coin shows tails, then they go to the football together. And they would give probability 0 to get in to different places. So this would be a solution which is equitable for the two Nash equilibria in this game. And the expected reward under this probability distribution for both of the players would be 1.5, much greater than 2/3. So a correlated strategy for the players gives the joint probability for a strategy profile, which is not necessarily a product of marginal probabilities for all the players. So in fact, mixed strategies, the mixed strategy profiles are a subset of correlated profiles. And that is why both agents in the correlated case would receive higher utilities than in the uncorrelated case. Why is that? Once again, because now we are in the superset of the strategies, so we can do better. We have more possibilities to increase the utility of the player. Okay, so generally, we cannot go worse than in the Nash equilibrium. Okay, and the outcome, in some sense, is also more fair than either a pure strategy or a mixed strategy. So those correlated devices, the mediators, that's another name that you can read in the literature for them. The mediator, the communicates between the players and give them an advice what strategy profile to play together jointly are pretty useful. Another point about that is that indeed if the advice of the mediator is to play the correlated strategy theater, for instance, then there is no incentive to each one of the players to deviate unilaterally from that strategy. Because if the advice says go to theater together, if I deviate and go to football and my opponent goes to theater, then we both get 0, right? Rather than I get 2 or 1 if I do follow the advice of the mediator. So the essence of this concept is that basically each one of the players get a signal, some advice from the mediator about which joint action to play, and none of them can gain by ignoring this advice and deviating from the strategies. Usually we would assume that these signals are private, given separately to each one of the agents. Sometimes it may be just a common knowledge given to all of the agents and publicly known. So, correlated strategies, once again, is a joint distribution over all the strategy profiles. In the 2-player games, it's just pairs. And in the Battle of Sexes, we can give it as half-half for 2 Nash equilibrium points and zeros for the other ones. So I can write this down for a 2-player 2 strategy game as given the probabilities P1, P2, P3, and P4 for the 4 strategy profiles that we have, so that the sum of the probabilities is 1. And the correlated strategy would be the combination of all, would be just this probability distribution over all strategy profiles rather than individual strategies of the players. Okay. And now the strategy, the combination of strategies A and C is split with probability P1 and so on. The expected utility of each player was given as an expectation under this probability distribution, so you take the utility of a given player in the P strategy profile and take it with the corresponding probability. Right. In the mixed strategy case, instead of those probabilities, we just have the product of marginal probabilities for both players. Right. So now we have joint probability, which is not necessarily independent distribution. Now, if we have probability 1 for one of the strategy profiles, that means that we play that P strategy profile in the game. Okay. And if this correlated strategy is given in the form of products of marginal probabilities for the 2-player, then it actually corresponds to a pair of mixed strategies. So that one of the players play one of the strategies probability P, and another one plays one of these strategies probability Q. Say, the set of correlated strategies is an extension of the set of mixed strategies, and in general, we need communication to attain a correlated strategy. So we need some device that would give a signal to the player so that they know what to play. However, the agreement between the players to play that strategy is not binding. They don't sign any contract. Okay? They are given an advice, and they just apply their rationality to decide whether to follow the advice or not. And the correlated equilibrium says that actually there will be no incentive for the players to not follow the advice. The extension of the definition of the correlated strategy is straightforward to n-player game and m strategy game. Say we had the set of strategies, pure strategies, SI for player I. And you remember that a mixed strategy was a probability distribution over that set. And the mixed strategy profile would be a combination of those mixed strategies for all the players. Now what happens in correlated strategies? So we have the set of pure strategies for all of the players. The combination of all of them would give us a pure strategy profile. So that's the set of all pure strategy profiles. And now we take a probability distribution over the set of profiles instead. Okay. Now, of course, this set is contained in the set of correlated strategies. So here we only have distributions which are independent of the players. Here we would have also other distributions over the strategy profiles. So when we talk about what is the mediator and what are the signals that the agent have, how can we somehow describe this situation, give a story that would underline it. You can think that in the setting there would be some random variable that has some common known probability, and then each of the agents get a signal about the realization of that random variable. Okay. And now the signal is correlated with the random variable's value and with the signals which are received by the other players. Now, standard games with mixed strategies are a special case of that, in some sense a degenerate case where the signals of different edges are probabilistically independent. So we can consider n random variables, one for each player. Okay. And those variables have some joint distribution. Okay. Now, the nature chooses some realization of those variables, and the agents get the signal about that generalization. So what is a correlated equilibrium formally? So if we have a game in a normal form as before, agents, pure strategy sets, utility functions, a correlated equilibrium would be given by the following combination of parameters, V, pi, and sigma, where V is a tuple of random variables, each one for the player. Okay, so you may think of it as an abstraction, but there is something that is related to the setting in which the players play their game. Each one of them has its respective domain, D1, D2, and so on, Dn. And then we have some joint probability distribution over all of those variables. Okay, so pi is a set of probability distribution, the vectors of size n as the number of variables, the sum of the elements in the vector must be 1. That's probability distribution. Now sigma for each one of the players is a mapping that maps the value of the random variable to a particular pure action of the agent. Now, what would be an expected payoff, an expected utility to a given player in this setting? So under the distribution, so we look at all the points in the domain. So that's joint values for all the variables. We take the corresponding joint distribution, and we look at the utility of a given player in the combination of strategies. Now, each strategy for each player is given by the mapping of the realization of the random variable to the set of pure actions. Okay. So the argument under U is just the combination of pure strategies now. right? Which depend on the realization of the random variable. You take those utilities and you take them with the probability distribution, the joint probability distribution of that. A given combination, so what are the strategies for the players here? What is the correlated strategy for the player? That's actually the very same mapping. How do I map the signal that I get to an action that I take? So correlated strategy would be an equilibrium if the expected payoff that I get there is greater or equal than an expected payoff in any other mapping that I could take, given that the others do what they do. So the essence of an equilibrium is exactly the same. We just replace the probabilities with joint probabilities of the profiles rather than products of individual probabilities. Questions? Now, note that we define those mappings as a function that goes from the domain of a random variable to the set of pure actions. Equivalently, we could have defined it as a mapping to the set of mixed strategies, but that would not add any greater generality to the case, because anyway, we would consider the joint distribution of the strategy profile. So we would mix over all of them anyway. Okay. So it's easier than, it's simpler to define the mapping to the set of few strategies. Now for every Nash equilibrium, we can always construct its corresponding correlated equilibrium. And that's why knowing that the set of Nash equilibria is not empty, we would conclude that the set of correlated equilibria is never empty as well. So for every Nash equilibrium, there exists some corresponding correlated equilibrium. How we would construct that? That's pretty intuitive, right? So given some mixed Nash equilibrium, we would look at the mixed strategies which are in the equilibrium, take their product, that would define as the joint probability of the strategy profile, and this way we define the corresponding correlated strategy. Okay. So if we have some Nash equilibrium, then we can just define the domain of each variable for each player as exactly the set of their few strategies, and then we let the joint probability to be the product of the mappings for all the edges. So how do we choose that mapping? We choose that exactly as the mixed strategy of the player. For instance, in the Battle of Sexes, where we had unique mixed strategy Nash equilibria, 2 thoughts, 1 thought, 1 thought, 2 thoughts. So the correlated equilibrium of that game would be given by probabilities 2/9 for theater theater, 4/9 for theater football, 1/9 for football theater, and 2/9 for football football. You just take the product of the probabilities given by the mixed strategy Nash equilibrium. But there are also others. There are also other correlated equilibria, like this one that we looked at the very beginning, which do not define, which do not correspond to any mixed strategy Nash equilibria in the game. So the set of correlated equilibria is strictly larger than the set of Nash equilibria, and that's why the concept itself is weaker than the concept of Nash equilibria. Okay, so that's the weaker solution. We have more correlated equilibria than we have Nash equilibria. Now the advantages of correlated equilibria are the following. quite a natural concept. It's quite natural to assume that the players would think in terms of joint probabilities of a given combination of strategies rather than define marginal probabilities and assume that the players would take their actions independently of a given probability. So that's a natural concept. It always is guaranteed to exist. Another thing which is also very convenient, that if we have some two correlated equilibria, we always can combine them and achieve a new correlated equilibrium. So what happens is that given two points, any convex combination of them would define a new correlated equilibrium. Do I have to explain what a convex combination is? Well, very basically, so graphically, we said last time, what is a convex set? If we have 2 points and we take an interval in between them, all the points on the interval must be elements of the set. Right? So the points on the interval that connect between 2 points are all convex combinations of these 2 points. How is that given? That point A, that's point B. Well, in Rn is defined as vectors. Yeah, but let me make it simple. Take some parameter alpha between 0 and 1. Well, it doesn't have to be strict. Alpha A plus 1 minus alpha B is a convex combination that defines actually any point here, depending on the value of alpha. Okay? When it's 0, you get point B. When it's 1, you get point A. When it's in between, you get all the points in between. Okay. So now, look, we said any convex combination of 2 correlated equilibria is a correlated equilibrium. So if we have 2 correlated equilibria, we know that the interval that defines them, all of them are correlated equilibria. That means that the set of correlated equilibria can be either a singleton, it's never empty, we said, because it must contain at least one mixed strategy Nash equilibria. So it is either just 1 point, or if there are at least 2 points, then the whole interval between them must be there. So it must be a convex set always. If there are more than 1 point, there is a convex set. And then that must be also an infinite set. Because if there are at least 2 points, we have the whole interval, that's a continuum of points. So it says either 1 or a continuum. Any questions here? Another good thing about correlated equilibria, you can find them in polynomial time for any number of players and strategies by using linear programming, because the conditions for a correlated strategy to be in equilibrium is the set of linear equations of inequalities. Okay. So we just have to solve a linear program. And that's why it can be computed efficiently as opposed to Nash equilibria, which is a subset of those. And you can find the details in this paper, which probably I will cover a bit next week. And we have 5 more minutes for this thing. Epsilon Nash. Another concept, based on another principle, and the principle is sometimes we would not expect, sometimes we would assume some inertia on the players, meaning that they would not change their strategy to another strategy if the gain from this deviation is not greater than some given value. So it could be the case that I have a strategy that would give me a better utility. But if that better utility is better just for a tiny bit, then probably I would not make a move. Say a strategy profile for a given value epsilon, some positive value epsilon, and epsilon Nash equilibrium would be defined very similar to n Nash equilibrium, but that would be a strategy profile, so that for every player I and every his strategy S prime I, what he gets under playing Si is at least as good as what he would get under playing Si prime minus that epsilon. Okay, so it could be the case that this value is actually less than that utility, but it's not less than that by more than epsilon. So this is a weaker notion that a Nash equilibrium. Now this is reasonable because indeed some players may be indifferent to small changes in their utility, so there is some inertia in that. And of course, epsilon Nash equilibria always do exist, because in particular Nash equilibria are epsilon Nash equilibria for epsilon equals 0. And every Nash equilibrium, in fact, is surrounded by a set of epsilon Nash equilibria. So there are many of them around every Nash equilibrium. But more than that, this solution actually may be preferred to Nash equilibrium because it's also easier to compute. Why is that? Because in the games where we have more than 2 players, we may have Nash equilibria which are given by irrational numbers. So some probability distribution that correspond to Nash equilibria will be given by irrational numbers. And that's what makes computation not easy. Now, if around each Nash we have some area of epsilon Nash equilibria, in each whatever small interval like that, well, neighborhood like that, we always would have those which are given by rational numbers. So it's computationally easier to find epsilon Nash rather than Nash. However, we cannot really say that epsilon Nash equilibria approximate Nash equilibria. Why is that? So that's true that around every Nash equilibrium we have a neighborhood of epsilon Nash, but we also would have epsilon Nash equilibria which are very far from any Nash equilibrium. Okay, that's why the set of epsilon Nash is not really an approximation of Nash equilibria. Let's look at this example, for instance. We have a unique Nash equilibrium there, down and right, that gives the utility of 500 to both of the players. And this also, of course, is an epsilon Nash equilibrium. But we also have another epsilon Nash equilibrium, up and left. Each one of the players get a utility of 1 there. Now, for column player, there is no incentive to deviate because he actually gets higher utility by playing left rather than right, given that the raw player plays up. For the raw player, if he deviates to down, he will get a greater utility, but only by half of the epsilon greater than his utility under playing up, so he would not do that under the condition of epsilon Nash. So UL is an epsilon Nash equilibrium, but look how far the utilities of the players in that epsilon Nash than in the unique Nash equilibrium in the game. Okay, so that's not really an approximation of Nash equilibrium. Also, some epsilon Nash equilibria would be very unlikely to arise at all in the play. So if player I does not care about a gain of epsilon, of half of the epsilon. Yeah, he probably would stay playing up, but then he might reason that, in fact, the strategy D dominates strategy U. Right? So he gets a higher payoff in the down strategy than in the up strategy, both in left column and the right column. So if the column player would pay attention to that, would reason that, okay, say my opponent has a dominated strategy in this game, which is up. So he would never expect the raw player to play his dominated strategy. So the raw player, realizing that, even though he does not care about the gain of half epsilon, will still play down, just because he would not believe the column player playing left. Okay, so some epsilon dash are just very rare to appear in the game. And I think we stop here, and I see you next